Hey, hi guys, welcome back to the channel. So in this particular video, we're gonna cover advanced audio feature extraction techniques theory. So this is gonna be a completely theoretical video. In future, I will make videos based on the code as well, where I will write code in Python to show how we can implement all these audio feature extraction techniques. So this presentation explores advanced audio feature extraction techniques. They are essential for audio analysis, music information retrieval, and speech recognition. So these are its benefits. Then these methods enables machines to hear and interpret sound effectively. So in most of the audio processing use cases, we are using this audio feature extraction techniques only. So before moving further, if you are new to the channel and if you want such information content, please make sure to subscribe to the channel and hit that like button as well. Let's move further. Let's see what is audio feature extraction. So basically in audio feature extraction, what we will do, first we will transform the raw data. So if you want to perform the audio feature extraction for the particular audio sample, we have to transform raw audio into the numerical representations. We can do this with the help of Python libraries like NumPy. So this process captures silent characteristics from an audio file, and same we can use in the further processing. Second thing we will do, it's capturing key characteristics. So basically we'll capture like frequency content, temporal dynamics, and timbre. So with the help of capturing these key characteristics, we usually make complex audio signals simplified. So we will retrieve only that data which is important for the audio pre-processing. And third will be like foundation for application. So whatever feature we will extract, right, this will be the base for the audio related applications like music genre qualification, speaker recognition, like that. Let's move further. In this particular slide, we start covering all the techniques. First is spectral features. What we will do in the spectral features is first we will analyze the frequency distribution. So spectral features examine frequency distribution. Then short time Fourier transform shows frequency components over time. And this will be used for the feature extraction. The second thing is MFCCs and Chroma. MFCC is nothing but Mel-Frequency Cepstral coefficient, which is like mimic of human hearing. Suppose there is one audio file, how are human ears gonna uh, listen that, hear that? That same mimicking, it's done by MFCC. The thing is, they are effective in speech and music analysis, and the chroma features represent the harmonic content, and it will be useful for the chord recognition. Third thing gonna be spectral centroid and bandwidth. So spectral centroid indicates brightness. It differentiates instruments and genres. So spatial bandwidth measures frequency spread, and this will be the crucial for the timbre characteristics. So this was all about the spectral features. Let's see the next technique. The next technique is temporal features. There are total 4 types of temporal features which we can retrieve. First is ZCR, nothing but zero crossing rate. This ZCR measures how often the signal changes sign, and it will be useful for distinguishing voiced and unvoiced speech segment. Suppose if you are having an audio file, there are some uh, silent areas in that audio file, pauses are there. Then to remove those pauses, we can use this ZCR or zero crossing rate. So this was its application. The second thing is root mean square energy, or nothing but RMS. So RMS represents signal intensity over time. This is an indicator of sound level and activity within the audio. The third thing is audio's tempo and beat tracking. So this in this particular thing we detect the rhythmic pattern in music. It will be crucial for music information retrieval or DJ applications. And the fourth thing will be onset detection function like ODF. It will be helpful for identifying note onsets or transit events. It forms the basic for rhythm analysis and music transcription. So this was all about the temporal features. Let's move further towards the Cepstral features. The Cepstral features contains Mel-Frequency septal coefficient MFCCs. These are derived from the septums. These are robust to noise and speech variations, and these are dominant in speech recognition systems. I have created a end-to-end speech recognition system. Even I have published a IEEE paper as well. If you want that, just comment down. I will give you the link. The second thing is spectral envelope representation. So we can represent MFCCs the spectral envelope, like typically 13 to 40 coefficients per frame, and those coefficients will contain the important data related to that particular audio file. Based on these frames, we can retrieve the characteristics and train our models. The third thing will be linear prediction septal coefficient LPCCs. So this linear prediction septal coefficients based on linear predictive coding LPC is like a more computationally efficient than MFCCs. MFCCs you will have multiple directions, but in linear LPCCs there will be only single channel, and it will be used in speech coding and speaker recognition. So this is similar to the MFCCs but with limited directions. So this was all about the Cepstral features. Let's see deep learning based features. We are having AI ML, right? Artificial intelligence or machine learning. There we will create different AI models, machine learning models. So based on that machine learning models also we can use the feature extraction techniques. First is convolutional neural networks or CNN. So convolutional neural networks automatically learn the relevant features from the spectrograms, and these are effective for environmental sound classification and music genre recognition. The second thing is recurrent neural networks or RNNs. This captures the temporal dependencies in audio signals, and these are suitable for speech recognition and music structure analysis. The third thing is hybrid approach, where we are combining CNNs and RNN for the improved performance, and we can achieve whatever result we are having. And the fourth thing is transfer learning. So we can use the pre-trained models, we can fine tune them for audio tasks, and then it will result in the reducing training time, and it improves the generalization capabilities. So these were the deep learning based features. Let's see what are the challenges in this future audio extraction techniques or audio feature extraction techniques. First is high dimensionality. When you consider audio data present is significant dimensionality. There are multiple dimensions. So when you have to retrieve the features, you have to consider each and every dimension. Then only you will be able to succeed. So that is the first challenge. The second challenge is noise sensitivity. Wherever you capture an audio file, you will see there will be a lot of noise, lot of other noises as well, even environmental noise or human noises, car noise. There are multiple noise. So before extracting the audio features, first you have to remove the noise, and then you have to perform the further computation. So this noise sensitivity also impact the accuracy. Third thing is computational complexity. So feature extraction algorithms are computationally complex. They require significant resources. It's like you are training a machine learning model. It requires a lot of resources. So same with the computational of audio files. And last thing is domain specificity. So learned features are often domain specific. Suppose if I am training a AI model or machine learning model for music genre music genre classification, then I can't use the same model for the speaker recognition and the vice versa. So this about the domain specificity. If you're training a model for one particular domain, you can't use for the other one. So these were the challenges and limitations in audio feature extraction techniques. Let's see what are the future trends in the audio feature extraction. First is self-supervised learning. So we can leverage unlabeled data and this learns global robust audio representations. Second thing is expandable AI. So AI nowadays occupying every space, so we can use AI for the feature extraction. Third is multimodal fusion. We can combine audio with other modalities. This enhances analysis capabilities. And last is edge computing. We can deploy algorithms on devices. This will enable real-time applications. So this will be the future tense in the audio feature extractions. I think that's it for this particular video. If you are having any further doubts, make sure to comment. I will try to reply back. If you want this presentation, again comment down. If you are new to the channel, make sure to hit that like button and subscribe to the channel for more such informative videos. That's it for this particular video. Thank you.